Hi everyone, my name is Mudawat Lakshman of third semester CSE F section. Today I am going to explain about enumerating anchored permutations with bounded gaps from the subject Mathematics for Computing. So let's dive into the introduction part. Introduction to anchored permutations with bounded gaps. This presentation explores the enumeration of anchored permutations where gaps are limited by a specific bound. Anchored permutations are permutations with a fixed starting point, often the first element. Bounded gaps restrict the difference between consecutive elements, adding combinational constraints to the permutations counting process. So here we focus on the concept of anchored permutations with bounded gaps. A permutation is simple a way of arranging elements in a particular order. But here we apply specific restrictions. An anchored permutation begins with a fixed element, usually the first element of the set. Along with that, we introduce the idea of bounded gaps, which means that the difference between consecutive elements cannot exceed a certain fixed value, denoted by k. These restrictions make the problem much more interesting because it reduces the number of valid permutations and creates a unique class of sequences. Our goal is to explore how these restricted permutations can be enumerated, what methods are used to count them, and why they matter in computational mathematics. So, let's dive into the basic definitions and the notations of these permutations, anchored permutations with bounded gaps. Here, a permutation is an order of arrangement of distinct elements from a set. Anchored permutations have a fixed initial element which typically denoted as one or another specific value. Bounded gaps mean that for any consecutive pair, the difference in their value does not exist a predefined limit of k. Before diving deeper, it's essential to define the terms clearly. A permutation is an order of arrangement of distinct elements from a set, usually we call 1, 2, 3 to n. In anchored permutations, one element is fixed at the start. Most common, the number is 1. Okay. For bounded gaps, we define a value of k. And for any two consecutive numbers in the permutation, the difference between them cannot exist this k. For example, if k equal to 2, then consecutive numbers in the sequence cannot differ more than 2. Using this notation, we can formally analyze the classify permutations into those are valid and those not under this restriction. And here next we go for the significance of the study. What is the significant study of these anchored permutations? Enumerating such permutations has applications in sorting algorithms and data organization. The constraints model real-world scenarios where steps into transitions are limited. Understanding their enumeration helps in analyzing the complexity and structure of the constraint permutation classes. Now, you may wonder, why do we study the restricted permutations at all? The significance lies in their applications. These structures are not just abstract mathematical puzzles. They model real-world problems. For instance, in sorting algorithm or data organization, steps may be limited by maximum allowed transition. Similarly, in network routing or scheduling problems, constraints are often imposed on the jumps between states. By enumerating these constraint permutations, we can better understand the complexity of the process and the design algorithm to handle them. Hence, the study is both theoretically and practical value. Okay. Next, let's take a basic example of the bounded gap permutations. For example, with a bound of 2, the permutation 1, 3, 2, 4 is valid if all successive differences are most 2, right? The permutation 1, 4, 3, 2 would not be valid if the gap exists the set bound at any point. Small cases help illustrate the constraint and guide the development of enumeration formulas. Here, let us take an example here. Okay, the concept is clear. To make the concept clear, we take an example. Suppose we fix the bound k equal to 2. Okay, consider the permutation 1, 3, 2, 4. The sequence is valid because the difference between successive numbers are at most 2. On the other hand, the permutation of 1, 4, 3, 2 is not valid if the gap between 1 and 4 exceeds the limit of 2. Working with such small examples helps us visualize the restrictions more clearly. They also provide a foundation for developing general formulas and techniques to count valid permutations in logic cases. And let's dive into the constraints and their formalization. How the constraints have to followed here, and what are the formalization of these anchored permutations. Formally, a permutation pi of length n is anchored if pi of 1 equal to 1. The bounded gap condition requires pi of I plus 1, pi of I plus 1 minus pi of I are less than or equal to k for all from 1 to n minus 1. These constraints defines a set of all permutations known as bounded permutations. Here, To make decision more rigorous, we need a formal decision. A permutation pi of length n is called anchored if the first element is fixed. Okay, that is I of 1 equal to 1. The bounded gap condition is written as I of I plus 1 minus I of 1 or less than or equal to k for all I from 1 to n minus 1. These conditions together define a special class of permutation known as bounded gap anchored permutations. Formalization is important because it allows us to move from initiative examples to precise mathematical statements which are necessary for enumeration proof based approaches. And next dive into connections to permutation patterns. Anchored permutations with bounded gaps can be viewed through lens of permutations, pattern avoidance. Such permutations avoid certain large jumps representing pattern restrictions. Pattern-based approach facilitates the applications of combinational enumeration techniques. Okay, so here connection to permutation patterns. Another way to understand bounded gaps anchored permutation is through permutations pattern avoidance. Okay, normally permutations may exhibit large jumps between consecutive elements, but in bounded gaps permutations such large jumps are forbidden. Okay, in other words, we can say that they avoid certain patterns. This perspective allows us to apply existing techniques from the study of permutation patterns as well as established fields in a combinatorics to analyze the constrained permutations more effectively. Okay, and let's dive into the recursive structure and decomposition of these anchored permutations. So what are the recursive structures and what is decomposition in these thing? Okay, these permutations can often be broken down into smaller components with smaller properties. Recursive formulas can be derived by considering the position of the largest element. Decomposition aids in constructing dynamic programming algorithm for enumeration. A very powerful property of these permutations is that they can be often be decomposed into small pieces. For instance, by considering the position of largest element, we can break down a permutation into smaller anchored subsequences that they obey some constraints. This recursive natural enables us build enumeration formulas systematically. Such decomposition is not only mathematically elegant but also useful in decomposition of algorithms. Okay, particularly dynamic programming approaches to count permutations is efficiently. And let's go into counting methods overview. What are the counting methods overview in this anchored permutation? Like enumeration can be approached via combinatorial recursions, generating functions, or bijective proofs. When it comes to enumeration, several methods are available. One common approach is the recursive relation, where the count for n length permutations is expressed in terms of shorter permutations. Another approach is generating functions encode the counts into algebraic objects, allowing algebra manipulations, that is, which encode the number of valid permutations as coefficients in the algebraic series. In some cases, recursive constructions often lead to recurrence relations suitable for computational enumeration, that where we establish one-to-one correspondence with the other combinatorial objects are also employed. These methods provide different perspectives and tools for solving the enumeration problems here. Okay, and next, generating function approach. How we generate the function approach? So the generating function approach for bounded gaps, permutation encodes the number of permutations for each length n. Okay, it often satisfies a functional equation derived from the recursive structure of the permutations. Solving these equations yields explicit formulas or recurrence relation for enumeration. Here, the generating function approach is particularly powerful. Okay, essentially, we create a function where the coefficient of expo n represents the number of valid permutations of length n. This function often satisfies a recursive or functional equation derived from the structure of the permutations themselves. By solving the functional equation, we can obtain explicit formulas or recurrence relations. This approach connects the problem to algebra and analysis, offer deep insights into behavior of bounded gap enumerations and bounded gap permutations here. And next, let's go to recursive relations and closed form formulas of these enumerations and permutations. So recurrence relations can often be derived from the recursive decomposition of anchored permutations. Here we are saying that recursive relations arise naturally from the decomposition of permutations. For example, by fixing the largest element and analyzing where it can be replaced, we can express a count of longer permutations in terms of shorter ones. Like closed form formulas are obtained for specific bounds, especially small values of k. These formulas facilitates direct computations of permutations count for given lengths. Here we can express the count of longer permutations in terms of shorter ones in some special cases, particularly when the gap bound k is small. When the gap bound k is small, closed form formulas can be derived. These formulas allow direct computations without recursion and make it easier to analyze the growth of permutation counts. Okay. Next, we'll dive into applications of enumerated bounded gap permutations. What are the applications and where we use these things and all. So these permutations model constraints, sorting process and data structures. They are relevant in study of restricted permutation classes and their combinatorial properties. Insight from enumeration aid in analyzing algorithm with limited step sizes or modifications. So the applications of these study extend to several domains. In computer science, constraint sorting process or limited step algorithms can be modeled through these permutations. In combinatorics, they represent a restricted class of objects that helps us understand broader structural properties. Furthermore, in practical scenarios such as data transmission or scheduling, the bounded gap property models real world restrictions. Hence, the enumeration results have theoretically as well as applied significance. And let's dive into open problem and research direction. So, extending enumeration results to larger bounds and more complex constraints remains an active area. Investigating the asymptotic behavior of the counts as n grows is a key challenge. Connections to other combinatorial objects such as lattice paths and trees offering promising research avenues. Okay? Although progress has been made, several open problems remain. For example, extending enumeration results to larger bounds k and understanding asymptotic behavior for larger n are ongoing challenges. So there are also connections to other combinatorial structures such as lattice path, trees, graphs, models that remain to be fully explored. These open questions represent exciting research opportunities for mathematics and computer scientists alike. And let's dive into what are the key concepts we have discussed in these things. To summarize, anchored permutations with bounded gaps combine fixed starting points with the different constraints. Enumeration relies on recursive structures, generating functions and algorithmic methods. Here, anchored permutations with bounded gaps combine two simple ideas. First one is fixing the first element and restrict the difference between consecutive elements. Despite being simple, they form a rich mathematical structure with interesting enumeration problems. Recursive methods generating, on the other hand, recursive methods generating functions and algorithmic approaches are central of their study. The insight gained from these work not only enrich combinatorics but also aid in this analysis of the algorithm and system with the inherent constraints. Okay, understanding these permutations enrich the broader field of constraint combinatorial enumerations. The next conclusion and the final remark. In conclusion, the study of bounded gap anchored permutations offer valuable insights into constraint combinational systems. Techniques developed here have potential to impact algorithm design and theoretical combinatorics. Continued research will be deepen understanding permutations, classes, and their numeric properties. Here, in conclusion, we can say that the study of bounded gap anchored permutations demonstrate how small restrictions can lead to complex and fascinating combinatorial structures. The enumeration techniques developed for these problems are broadly applicable, impacting both theoretical mathematics and algorithm designs. Continued research in these areas promises to uncover deeper connections with other combinational objects and may even inspire the approach of solving real-world computational problems. Okay, this is all about